This is a bit of an experiment. This is the poster presentation session. My name is Tim Pedley. I'm from the Department of Applied Mathematics and Theoretical Physics next door. And I've been brought in because I'm such a fierce chairman. So, there are poster sessions today, there are poster sessions tomorrow. Today, poster session 1, there are 24 posters listed. The presentations, we'll take them in order. We will do all the presentations this morning so that the afternoon session is available for people to go and look at the posters. The purpose of these sessions this morning is for the presenters to advertise their poster, not to tell us everything. They have a maximum of 2 minutes, and at the end of 2 minutes, this will go off. Which may not.
We were told originally 3 minutes.
Yeah, it's 2 now.
Some people have been told 3 minutes, some people have been told 2 minutes. In order to fit 24 people into 1 hour, including a little bit of interchange time, it will be 2 minutes when this will go off. And you get a maximum of
2 slides.
2 slides, I believe, but they're all loaded up, so we'll see how it goes. But this,
I thought you did only 1 slide.
1 slide, okay. Okay, well, 1 is less than 2. A maximum of 2 means 1, or 2. 1 slide is fine. So, we're going to see how it goes, and the first presenter is, I'm going to do that in a minute. Wait. The first presenter is Kojiro Yano, and go for it. This is now started.
It has started? Yeah. Okay. So, hello, my name is Kojiro Yano from Dant. So I'm his colleague, actually. This is actually not the heart, of course. This is the pancreatic acinar cell. The pancreatic acinar cell is the cells in pancreas, which is responsible for secreting digestive enzyme. So it's not the beta cells which secrete insulin. Then pancreatic acinar cell is quite interesting because it has got this polarized structure where you have got granules on the top and the rest of the region at the bottom. It has got this localized calcium oscillation, which you can see here. So I have modeled that using a kind of shared 3D model with the rotational symmetry. Then what I have done is to make sure that the symmetry is preserved. Then also the emphasis is to make sure that the diffusion of the intracellular intra-ER calcium is preserved, because it is very important for the for this cell type to diffuse calcium from this bottom region to the top region so that the calcium signaling can be maintained. Then I have also looked at the coupling between calcium oscillation and ATP, because actually this oscillation is maintained by the IP3 receptor. The IP3 receptor is very sensitive to calcium concentration. IP3 is very sensitive to the ATP concentration. So I believe there is a coupling between ATP concentration and IP3 receptor activity, which will affect the calcium oscillation. And I have also looked at the combination of the type 2 and type 3 IP3 receptors, because I realized actually having just one IP3 receptor doesn't reproduce everything in pancreatic acinar cell. So I have actually added 2 types of receptor, type 2 and type 3 IP3 receptors. And I have found that the combination of the 2 reproduce much better the shape, spatial pattern and temporal pattern of the calcium oscillation. Is that it? Okay.
If they do it in the time. Okay. There you go. It works. The next is Sanjay. Okay. Right. You've just got the one?
I've just got the one.
Okay.
Many thanks. And this is a sensitivity analysis that we propose now for biophysically detailed cellular models of cardiac cells. And the motivation for such a quantification or objectification of the parametric influences on modeling responses will primarily feed into several aspects of simulation and development, one of which is cell model development, objective cell model development. And therefore, what we propose is that the quantification of parametric influences on modeling responses, like minimum potentials, maximum potentials, action potential durations, can be robustly and globally done via a neutral information index, wherein correlation is normalized by the entropy of the parameters and modeling responses. This measure, the mutual information measure, is quite robust and can be applied to all models, be they linear or nonlinear. And nonlinear models have a very typical feature of multimodality, even as we have perturbations of parameters which are uniformly distributed. As we have seen throughout the last few days and throughout this month, Dennis Noble and others have mentioned how parameters are important and often overdetermined, and so such a indexing scheme will objectify and quantify the effects of parameters on modeling responses. An immediate application of such a quantification of modeling responses or parameters on modeling responses is a parameter estimation of any free parameters that we may have using a very simple scheme. However,
Time's up. Now you know what to look at in the poster. All right, the next one is Daniel Olmos.
Thank you. Well, my name is Daniel Olmos, and I'm from the University of Sonora in Mexico. So I'm just want to talk a little bit about the main purpose of this talk is of this poster is to find the properties of by such a spiral wave can attach to an obstacle. Okay, so the main thing is that if you have a spiral wave that it is meandering in a medium, it is a completely different if you have a spiral wave attached to an obstacle, because they represent a different kind of arrhythmias. And if you have a spiral wave attached to an obstacle, it will mean that you have a more controllable arrhythmia. So basically, what is this work about is just I consider two models: the Fitsu-Nagumo, just a modification, and another one which is the Wheeler-Reuter. And the thing is, I consider this Fitsu-Nagumo is just because it is actually the way I found, the things I have found is just that the geometry of the obstacle is very important, also the size. So it is very important to get attachment of the spiral wave to the obstacle. So basically, in this work, I just try to find some properties that will give a little bit if when you get attachment and when you don't get attachment. So that's a little bit about it, and yeah, that's all. Yeah. See my poster, please.
Okay, and the next one is Esther. Oh, I've just done that.
Yeah, okay.
You can, yeah. Okay. Right, go for it.
Okay. So I will present this study that has been done at the Computing Laboratory, the University of Oxford. So in this study, we are interested in investigating variability in repolarization and see how introducing variability in the model, in the cellular models, can help us understand conditions that are associated with high arrhythmic risk. So we take a multi-scale approach. We start modeling fluctuations at the ion channel level. Then we go into a cellular model to see variability at the action potential. And then we go into tissue to see how coupling between cells has an effect on variability. So at the ion channel level, what we do is to consider an ionic model and then incorporate the stochasticity in the opening and closing of the channels. So we consider an additional random term, which is we can demonstrate that it is inversely proportional to the number of channels that we have associated to the current. And that is why we start introducing stochasticity into the IKS current. So we validate the model using experimental data that we have available for human and for other species, both in terms of number of channels, unitary current, and so on. So once we have the ion channel model with the stochasticity, we go into a cellular model, and we see the effect on temporal variability in the action potential. That is how an action potential varies from one bit to the next. And also, we investigate cell-to-cell variability. That is how the action potential may vary from one cell to the neighboring one. And we see that the ranges of temporal and cell-to-cell variability that we simulate with the model are within the physiological range. Well, these ranges of variability that we see at the cellular level are then reduced when we go into tissue simulations because of the effect of coupling. And in the final part of the study, what we do is to consider how this variability has an effect on arrhythmic risk markers such as the generation of early after depolarizations or alternates.
Okay, the next one is being presented by Andrew Foulkes, who's the fourth author on this title.
Right, thank you. So subject to a small perturbation, a spiral wave may drift. Now, the drift velocity can be calculated either through experiment or through some tedious numerical computer simulations. Another way that it can be calculated is through computing convolution type integrals of the spiral wave's response functions with the perturbation. Now, response functions are the critical eigenfunctions of the linearized adjoint operator. Now, we offer a general robust method to compute the response functions fast and accurate. And what we present here is some drift calculations together with some response function calculations. So in the picture in the middle there, on the left-hand side column, we've got the actual spiral wave solution. The next three columns are the Goldstone modes, and the far right three columns are the actual response functions. Now, the differences between the Goldstone modes and the response functions was in no way assumed in the numerical calculations. So one of the applications then of response functions and the main purpose of this particular poster is to calculate the drift velocity. So in the bottom three pictures here, I'll start with the left-hand side. It's just a snapshot of the spiral wave, which is drifting due to resonant drift in the Fitzhugh-Nagumo model. And the white line there is the tip trajectory. In the middle picture, which is one of the main results of this particular study, is the relationship of the drift velocity on the amplitude of the perturbation. And you can see, well, it's much clearer in the poster, but for smaller amplitudes, the correspondence between the asymptotics, that's the integrals, and the simulations is very, very close. It's the difference is about 0.2%. And the final graph there is just a convergence test that we've conducted. Thank you.
Okay, next one's Andrew Cookson. Go for it.
Okay, so yeah, bit of a tongue-in-cheek title really. Could mixing be good for your health? Well, maybe. So fluid mixing has been hypothesized to be useful in preventing occlusion of bypass grafts and shunts from thrombosis. And Colin Caro and his colleagues proposed that if you use a small amplitude helical pipe to make your graft, then you'll get this mixing and help the patient live longer. So helical pipes have been studied before, but mainly analytical work, and so they haven't really looked at the parameter range that we're interested in. So what we've done here is a numerical study using some unnice coordinate mapping of the Navier-Stokes equation, spectral element method. So there's some information about that on the poster if you're interested. The key results, the first one was to look at a single pipe, as you can see up there, and study the mixing in that. And what we've shown is you can explain the mixing behavior relative to the velocity field using a sequence of reference frame changes. And once you've done that, this basically gives you this situation here. And we can say now, actually, we can use this principle illustrated here to generate much better mixing by combining in series helical pipes of differing helical radius shown here, and there's also some information about that on my poster as well.
Thank you. Right, the next speaker is Dr. Sivika. Oh, sorry. Not yet, don't worry.
Oh, good morning. Good morning. My name is Radoslav Sivita from the Department of Mathematics, University of Malmo, and my main interest in the asymptotic reduction of detailed cardiac models. Well, the aim is simple. Basically, we hope to obtain mathematical models which are simpler to analyze theoretically than numerically. And in order to do that, we have developed a consistent procedure of estimating the relative speed of dynamical variables, so we could decide which of the dynamical variables change significantly during a given stage of the action potential, and which of the dynamical variables could be treated as fixed parameters. And this procedure allows us to dissect, to split a detailed cardiac model into mathematically complete subsets of equations which describe the various stages of the action potential, for instance, the front, the plateau, the recovery stage, and so on. And here in my poster, I illustrate this strategy. So we start with a model of human atrial tissue, and we derive mathematically consistent, in a mathematically consistent way, model of the propagating front. We then use this model to obtain a very accurate, physiologically accurate description, condition actually, of when the spiraling wave will break up and self-terminate. So most of this work is done with Vadim Bektashev from the University of Liverpool. Thank you for your attention and welcome to my poster.
Okay, hang on. So our next presenter is Seville Orandi. Now,
My post is about mathematical modelling of unsteady blood flow in curved elastic arteries. And the motivation for this research is that atherosclerosis typically occurs in curved arteries or bifurcations, where the flow consists of complex secondary flows, flow reversals, or low shear flows. In addition, one factor often omitted from previous studies is the compliance of the arterial walls, despite the fact that compliance can cause up to a 10% variation in diameter during the cardiac cycle, and this can influence the wall shear stress. So our aim is to understand what the effect compliance has on the flow. So we consider a curved compliant pipe, where I is the inside the pipe bend and O is the outside the pipe bend. The flow is characterised by the D number, which is basically Reynolds number for curved flows, the Wormser number, the non-dimensional frequency, and the steady streaming Reynolds number. We expand in our asymptotic parameters. In the steady case, this is epsilon, compliance, and the D number, so they're both small. In the unsteady flow, we have compliance again, and now alpha, the frequency. And looking at our steady results, this is the magnitude of the resultant velocities in the cross-section of the pipe for the rigid case. And we see the traditional two-vortex structure, which Dean found, of counter-rotating vortices. Look at this vector plot, see the flows going around like this here, and that there. If you add a bit of compliance, you see that the effect is to shift the vortices towards the outside the bend here, which you can see again in the vector plot. So it's been moved towards the outside. Another interesting feature is that at one order, epsilon d cubed, we have 4 vortices in the flow. You can see the extra ones near the outside the bend. And if you want to see the unsteady results, please come see my poster.
right, next.
My name is Hans Dirks. I'm working in Ghent together with Marie Michel and Olivier Burness. So we did work on basic wave propagation. So I guess you all know the economic equation, or the velocity curvature equation, which is usually written as c is the plane wave speed minus d times the scalar curvature of the front. but we did an alternative derivation of this equation, and we obtain an extra numerical factor gamma, which is surface tension for France. And we have shown that in several models this can considerably deviate from 1, and it has implications on the critical radius of curvature when basing in tissue. So we can actually, based on response functions, we can actually calculate or predict the surface tension for a given model. And another feature that we have in our equation is that instead of just the scalar term d times k, here we have a tensor trace, and it accounts for all anisotropy in the tissue. So, and the way to derive this is by using the local rescaling, as Sasha Pavlov explained yesterday in his talk. Also, comparing with the spirals, we also here have like a localized feature of the wave fronts, which can be described in terms of the sensitivity function. And this time it's for fronts and that's for spirals. So if you want to know more, comments in that post.
Everybody's being very good. You'll get your lunch at this rate. Okay, the next one is Grigory Osipov.
So I am from Nizhny Novgorod Lobachevsky University from the Department of Theory of Oscillations. We are mainly studying different collective phenomena in heterogeneous medium. Here is the motivation of our study. Many systems in nature are complexly organized structures consisting of elements that possess different properties, and also we study heterogeneous elements of the same properties. These elements can be varied not only from the characteristics but also for the distribution of parameters. For example, one can mention here our heart. There are at least 3 cell types known in the heart, so-called pacemaker cells. We will speak about oscillatory behavior if we study these cells. Myocytes is so-called excitable cells, and fibroblasts passive cells. Actually, from the point of view of nonlinear dynamics, it's very interesting to find some interaction between of all of these cells and to study different phenomena due to this interaction. Using Vitsyu-Nagumo model and also Lu, Rudy, and Cole models, we study synchronization properties and wave dynamics in one-dimensional case, in two-dimensional case. We have found different phenomena about the synchronization frequency, the wave propagation, and so on. Welcome to my poster. Thank you.
Our next presentation is by Lucia Mirabella. Is this correct?
Yes,
Okay.
Okay, good morning. My co-authors and I would like to present our results in developing new strategies in order to solve efficiently the bi-domain propagation the action potential propagation in tissue. And we start from the fact that the bi-domain model is the most accurate model available in literature, but it has high computational costs. And so we found strategies to speed up the computations. In particular, we reformulated both the bi-domain system and the monodomain one, expanding the last. And you see here the graphical representation of the discretized matrix of the system. And we had the idea to use this extended monodomain as a preconditioner for the bi-domain model. And so we keep the accuracy of the solution, but we speed up the computation. And this preconditioner have been proved to be optimal with respect to the mesh size, and it also allows to save more than 50% on CPU time with respect to standard preconditioners such as IRU preconditioner. And the other idea we had was to formulate a new model that we call hybrid domain, because it lays in between the bi-domain and the monodomain one. And in fact, the upper right block that is empty in the extended monodomain, in this case, is sparser than in the bi-domain one. So as only some entries filled. and this hybrid domain change with time. So we define the model on the basis of a model error estimator that we found to control the error between the bidomain solution and the hybrid domain solution. And with this localizing this model error estimator, we can set up a model adaptivity strategy and building the hybrid domain model at each time step according to this model error estimator. And this strategy is able to reduce the deviation from the bidomain that we could find with the monodomain and allow to save computational time. Thank you.
Thank you. Right, our next presenter is Ayako Takeuchi. Keep that by your mouth.
Is one of the essential proteins in cardiomyocytes. Today, many groups have studied on structure-function relationship of the sodium-potassium bond, but there is no information exactly how the ion flows through the bond. In the present study, we visualize the ion pathway through the sodium-potassium bond by a combination of electrophysiological experiment and modeling. The first modeling is to construct a homology model of sodium-potassium bond based on circular structure in E2 beryllium chloride state, because this is the only one solid structure with open external pathway. Then we performed electrophysiological experiment to test the engineered systems to membrane impermeable MPSET. The amino acid residue whose system mutants showed MPSET responsiveness can be regarded as an ion pathway coordinating residue. Then we mapped the result on the homology model. It's clear that MPSET responsive residue, shown as red balls, form an unbroken pathway from external to internal side. Then finally, we performed the second modeling, a cavity search analysis called MOL. The calculated tunnels are beautifully surrounded by MPSET responsive residues, confirming the validity of the homology model. I will discuss in detail about the characteristics of each amino acid residue at the poster session. Thank you for your attention.
Okay, and the next presenter is Chae-Yong Cha, who will start.
To solve the ionic mechanism underlying the change of membrane potential, we developed a new method to quantify the contribution of the channel or transporter to automatic change of the membrane potential in mathematical cell model. After the linearization process, the membrane is represented with this circuit, and it can be reduced to the simple electrical circuit, and then the dVm/dt is represented with the simple equation, and then Vm is always tend to approach the VL, so we call it the lead potential. We calculate the lead potential during the action potential in SA cell and ventricular myocytes of Kyoto model, and because the change of Vm is attributable to the change of VL, so we define the automaticity of Vm with dVl/dt. Now we can measure the relative contribution of the channel by measuring how much dVl/dt is modified when the temporal dependency of the channel is selectively eliminated. The amount of the modification, the normalized, then it is defined as a relative contribution RC. We calculate the relative contribution during the depolarization phase in SA node cell. So you can see the temporal change of the depolarization of each channel. And you can see the negative contribution of the channel. It means that this current interferes with the depolarization. Thank you.
Next presenter is Yukiko Himeno.
I'm Yukiko Himeno, and I work with Dr. Cha on this lead potential analysis. In my poster, I will compare the result of lead potential analysis on different SA node models. This is the model of Himeno et al. 2008 from our group, and this is from Maltev and Lakata, published early this year. This is the membrane potential from the maximum diastolic potential to minus 20 millivolts, the slow diastolic depolarization, with the lead potential in red line. This is the profile of the lead potential analysis. The relative contribution is shown here. And this is the calcium, intracellular calcium, and the subsarcolemmal calcium concentration in green. The open probabilities and amplitude of the current system are shown at the bottom. The rapid component of delayed rectifier, potassium current, is the largest contributor in both models. We can see the sustained inward current here, which is very large in our model, whereas the INACA, the sodium-calcium exchanger current, is a major contributor in Maltev and Lakata model. And this current is specifically driven by calcium concentration in subspace. And we will verify the assumption of the subspace in SA node models in our presentation. Welcome to our presentation. Thank you.
Right, and the next presenter is Tony Chinchapatam.
Good morning. Today I'll be presenting our work on meshless methods for cardiac electrophysiology simulations, especially to model wave propagations. And the motivation behind this work is that because of the irregular geometries that we obtain from the cardiac images, we would like to work directly on the voxels of the images and without by alleviating the need to make a mesh. And the meshless method that I propose is based on radial basis function basis, and because of this and generalized differential quadrature method, and because of this, the adaptivity of this method is much more easier because nodes can easily be incorporated or removed from this methodology. I have presented this work for planar wave propagation as well as for realistic geometry in my poster. Thank you for coming.
That proves that it can be done in 1 minute if you really try. Anyway, now we've seen Andrew before, and he's going to tell us something else. Yeah.
I'm a bit greedy and I've got 2 posters. So this particular one's about drift and meander spiral waves, and the aim of this is what I did in my PhD project, and the aim was to understand the dynamics of drifting and meander and spiral waves, but in particular when they drift and meander at the same time. So we employed a quotient system reduction method, which led us to the description of spiral waves in a co-moving frame of reference. This means that the tip of the spiral wave is fixed for all time in a particular position within the domain of the wave, in the domain of the medium. So what this means is that the tip of the wave never actually reaches the boundary of the medium, so we can let the simulation run on for as long as we want. It also means that we can afford smaller domain sizes, which means faster computational time. Now, I was going to show a movie, but it's not actually working, I'm afraid. But basically, what the movie was showing, we had a drifting and meandering spiral wave with Fitzhugh-Nagumo kinetics, and the perturbation that we applied was an electric field. And what you would have seen was this particular meandering spiral was actually breathing. So it's a really, well, was a really nice movie. I've actually I've actually put it on my website. So if you find me on the University of Liverpool Computer Science website and just look at my research page, you can actually see this movie because it is a really nice movie. But basically, from the data that we've that we can get from looking at the co-moving frame of reference, is that we can study the limit cycles associated to spiral waves, and this is detailed more on the poster. So please visit my poster because you can't see my movie. Thank you.
Right, and the next presenter is Mauro Perego, who has a multi.
Yes. Yeah. So we devised a numerical scheme for solving the complex ionic models like the Lurudi one. So if we recast the ionic model in this form, where we have the transmembrane potential equation, the gating variable equation, and the concentrations equation, and exploiting the peculiar structure of the gating variables, we can, if we freeze the coefficient on over a time interval tn plus 1, we get the well-known Rasch-Larsen scheme. So the Rasch-Larsen scheme is very well spread. It is has good absolute stability properties. And in fact, it explicit but allows us to use a very large time step. The problem is that it's just a first-order scheme, so it's not very accurate. So our idea was to increase the accuracy by replacing the coefficient an and bn with an plus 1/2 and bn plus 1/2 with some approximations. And depending on the approximation, we get different schemes. And we prove that these schemes are second-order schemes, and they present good stability and positivity properties. And combining two of these schemes in a predictor-corrector fashion, we can get a posteriori error estimate and make a adaptation in time. And so, in order to reduce computational time, and we extended these schemes and applied successfully to the monodomain and bidomain models. So, if you're interested, poster 17. Thank you.
The next presenter is Sebastian Kritja.
Hi. This poster combines work I've done previously at the University of Karlsruhe and work I will now do at the University of Oxford at the computing laboratory. The combination between the two models which are developed there, you can see that in the title, which is towards dimensionless classification of cardiac fluid structure interaction. So what you need for dimensionless classification is, of course, a fluid structure interaction model. So this is work I've done at the University of Karlsruhe, which I will present on my poster. And what you can see is some kind of a structural model with fibers embedded in an isotropic matrix, a certain fluid domain with valves for the aortic valve and the mitral valve. And all this is done from MRI data, so we try to do these models in a patient-specific way. However, there are different models around, like, again here, the Karlsruhe heart model, which is from Karlsruhe. The open CMIS heart model, which is kind of my work at the University of Oxford. And what you get, it doesn't matter from which model, is you get some results, which you can see here for one time frame in cardiac cycle, which is quite interesting, and different visualization techniques. But the question is, if you have a whole bunch of cardiac models, or even the same kind of software approach, but different models in the same way, the question is how to define this in a dimensionless way. So if you do a dimensionless analysis, then you come up with dimensionless numbers, which is not surprisingly, if you do fluid calculation, you come up with the Reynolds number and the Wormsley number. But in that way, you also get some numbers for the structural part and even a combination for fluid structure and action. So if you're interested in fluid structure interaction numbers, please come to poster 18, I think.
Next presenter is Yuan. He is
Hello, my name is Yuan Ruan, and I'm a PhD student in Center for Medical Image Computing, University College London. And my project is a collaborative project between KCL, St. Thomas Hospital, and INRIA. The title is Non-Invasive Imaging of Cardiac Electrophysiology, and we choose boundary element method, which is a universally recognized method that already provide accurate solutions, fundamental solutions already satisfied the Lagrangian equation, and also although it's dense, in building the transfer matrix, it's a dense matrix, but it's still a good safe of computational cost. And as respect of activation time imaging, we are interested in explore different constraints comparing to a penalty term, and we choose to explore the Econo equation constraint, and the results and we use Newton method plus initialization using critical point theorem, and it's under discussion that the critical point theorem already gave a good initialization, and also the contribution of the nonlinear optimization it give a major contribution or not. So we are on the path of giving a good forward model.
Next presenter is Christian Wickler.
Hello. So my work is concerned with computation methods for fluid structure interaction, and the first part has been carried out at the Delft University, and the second part is currently being pursued at the Oxford Computing Lab. Both are concerned with fluid structure interaction. In the first part, it is where fluid flow, blood flow, and the structure, heart valves or arteries interact through a common discrete representation of the fluid structure interface. And we've been looking at the solution methods, assessing conventional solution methods, such as, for instance, subiteration, where one alternately solves a fluid and a structure subject to complementary interface conditions until this eventually converges. And of course, this is very attractive because you can reuse existing fluid and structure solvers, so this preserves software modularity, but it typically comes at the price of a lack of robustness, so there can be transient divergence or also inefficiency of this method because these iterations may take very long. So in conclusion, this subiteration we found is an attractive but rather poor solver, so therefore the idea was, rather than as a solver, let's use subiteration as a preconditioner to a Krylov method, in our case GMRS. So an analysis of what subiteration actually does has revealed that what it actually pursues is a solution of a nonlinear fixed point problem for the interface position. So upon convergence, you basically determine or you converge to the fixed point of this interface problem. And this is something that we then solve by a Newton-Krylov method and use subiteration as a preconditioner to the Krylov method to GMRS. And this is very effective and attractive because this acceleration, the GMRS, is applied only to the interface degrees of freedom, so it's rather inexpensive in computational cost and storage. Okay, if you're interested in further discussion, please come to poster 20. Thank you.
It's a bit small.
Okay,
It's
the
too
next
small.
presenter is Luca Gerardo from Lorda, who will tell you everything it's on.
Well done. In general, Italian people mess up with my family name, so that's good. Okay, that's going to be a very mathematical poster in the sense that we are dealing with an extension of what Lucia Mirabella was speaking about earlier. I mean, we have to solve. We have the bidomain model, which is the most accurate we have right now, and it is very expensive. So what we want to do, we want to reduce the computational cost. The hybrid domain that she was speaking about earlier is a good improvement. Nevertheless, it forces you to solve an extended monodomain in a certain sense. So what we want to do, we really want to switch the bidomain on only in regions where it's really needed, and solving just the monodomain one where it is not there is no need for a real accurate approximation. For instance, when the propagation front is not reached this region, there is no need for solving the bidomain when everything is at rest. It's just a waste of computational effort. So the idea is to use, and then the problem is how to couple those models, because on the interface region we have an equation, a system which has two equations, and a system which has just one. So we have to we devise at the level of the coupling a Schwarz algorithm, which comes from the domain decomposition universe, in which we had to devise a non-standard one, because there are two equations on one side and one on the other. So we had to devise proper coupling condition of Robin type, which are on the left side of this thing, and we've been able to optimize the Robin parameter in order to get better performance in convergence, and it showed very good robustness with respect to the mesh size on the interface. So this brings us to very promising results in view of completing the adaptive, the model adaptivity procedure that Mirabella was speaking about earlier. And if you want to hear something more about that, and you would like to have some mathematical rather than physiological thing, please come to poster 21. Thank you.
No, it's all right, Bob. Okay, the next speaker is Robert Whittaker.
Okay, hi, I'm Robert Whittaker, and I'm at the University of Oxford, and my poster's about work I've been doing with Sarah Waters at Oxford, and Matthias Heil at Manchester, and Oliver Jensen in Nottingham. And I've been looking at particular instability of flow through an elastic walled tube. This is mainly a fundamental problem, but there are applications for blood flow and airways and various industrial situations. My work has basically been asymptotic analysis, looking at a particular long wavelength, high frequency, small amplitude oscillation regime. And we've also been doing some numerical simulations. The people in Manchester have been running those, so we've got some comparisons for our asymptotics. And so far so good with that. The actual problem, we've got a Starling resistor setup in the top left up there, a flow driven from one side to the other, either via pressure drop or a prescribed flux. And I've looked at various aspects of the problem, started off looking at does the fluid flow in isolation with prescribed oscillations, solved the Navier-Stokes equations and found out about the fluid flow and the energy budget there. Then gone on to look at the wall mechanics and derived a classical form for a tube law, but derived it formally from shell theory. And finally put those two together to look at the case of free oscillations, coupling the fluid flow and the wall mechanics. And we can find out predictions for the normal modes and their frequencies and growth rates, and hence determine whether we've got this instability or not. And if you want to find out more, come and have a look at my poster.
Okay, now the next presenter is a replacement for,
Yeah, it's mine.
okay, hang on.
It's not the
A
title.
replacement for Oyvind Norbo, who is not presenting. And
My name is Danuta Makoviec.
Makoviec. There you go. Now you may start.
Yeah. So as it is a surprise for me to present the poster and the work. So that just two images which I extracted from my work. My basic interest is the leading pacemaker site, the origin of this leading pacemaker site. So the sites which initiate the electrochemical potential in the sinoatrial node. This beautiful figure is taken from the paper which is described on the in the top corner, and it's taken without permission. However, I suppose that authors do not complain. The authors are here. So this leading pacemaker site consists of about 1%. It's located somewhere in the center of the sinoatrial node, and position is not fixed. And the method of modeling is cellular automata modeling. So discrete time, discrete state, discrete space. The cell is represented as free state cellular automaton driven by stochastic oscillatory evolution, and cells are located in two-dimensional lattice, which is stochastic, and interactions are set in a stochastic manner at random, with preference to lateral, because the physiology says like that it's important. And what is most important is that we consider rewiring of local connections. So, however, this rewiring is still local. So the structure is not two-dimensional and is not flat. And we reconstruct the physiological properties. Thank you very much.
Last in this session, but not least, Anna.
Thank you. So my poster is about flow assessment in curved arteries. At the moment in clinical practice they use straight tube assumptions to estimate the blood flow. And a lot of arteries are curved, like the carotid arteries or the coronary arteries. And when you measure then, with, for example, an ultrasound scanner, the axial velocity through a curved artery, you will obtain an asymmetrical axial velocity profile. Therefore, we looked into the literature for some analytical approximations, and there seems to be a kind of correction term to give the equation for the axial velocity in a curved tube. We use this analytical approximations to estimate to use another estimation method for flows in curved arteries. And what we basically do is we take the axial velocity profile, divide it in two, and obtain of each of the half profiles the integral, and take the average flow of the integral. How good is this method? Therefore, we use the numerical benchmark of a curved tube model, where we could prescribe the inlet flow, so we know the flow, and could calculate the deviation of the physiome method and the cosine theta method. Oh, they didn't include my second slide, I think. Okay, so it doesn't matter. What I wanted to show in the second slide is that you obtain a 3 times better estimation of the flow. Physiome flow is at its best, like it gives a 15% deviation of the real flow when you go up to d numbers of 1000, which is a kind of physiological flow in the larger arteries. Well, the cosine theta method for both the symmetry plane and the plane perpendicular to the symmetry plane gives only error estimation of about 5%. Okay, thank you.
Well, I would like to congratulate all the presenters this morning on giving a clear advertisement for their posters in the time allotted. It's been very good, and and you'll get your lunch. And this means that the whole of the session from the end of this afternoon's lectures, from tea till dinner time, is available for examining the posters. And at least at the beginning of that period, the poster presenters ought to be beside their posters, otherwise the discussions will not be very fruitful. But of course, you want to see other people's posters. So after half an hour or so, there'll be a bit of mingling, I'm sure. But I think you will find that this afternoon is going to be much more profitable as a result of having been able to see these preliminary views this morning. So thank you, all the speakers, very much.